students, welcome back. We are now going to talk about the second type of energy. The second main type of energy is kinetic energy, energy of motion. Woo! So remember, there are two main forms of energy. One is potential energy, which is energy waiting to happen, energy that's stored. Second type is kinetic energy, which is energy of motion. Kinetic energy is the energy of motion, and we just abbreviate it KE. There are many different forms of kinetic energy, and one of them is the form of light. The first form of kinetic energy we're going to talk about is light, or electromagnetic energy, and it travels in waves. So energy travels in waves. Some examples of electromagnetic energy is obviously visible light. There's also X-rays. So if you've ever broken a bone, you had to get X-ray done. That's using light waves, using electromagnetic energy. There's also UV, ultraviolet light waves. There's also infrared, which is really heat. It's part of the electromagnetic spectrum. You have microwaves, you have gamma rays. So these are different types of electromagnetic energy. They're different based on their wavelengths. So if we look at waves, if you have a slinky at home, take it out and you can stretch it out. And if you move it up and down, you can see waves travel. And there's different types. There's transverse and longitudinal waves. Light travels in transverse waves, so it's up and down like this. If you make the slinky go up and down, that's transverse waves. Right, so here we have waves. This is a pattern. The tricky thing about this is we are looking at the side of the wave. We're looking at like the profile. In reality, waves are going to travel in all directions. So if I were to look at this from bird's eye view, if I'm looking down, if we look from the side, we see this pattern. But in reality, the waves are traveling in all directions, but when you look at waves and measuring wavelength and looking at the electromagnetic spectrum, we're looking at the profile. So we're not looking at the whole thing, we're just looking at one of these waves coming off here and the side view, the profile view of it. So this is going to be what it would look like. If you think of it, you throw like a rock in a pond. You can see the waves, when the rock lands on the water, waves will spread out. And that's the way waves travel. Wavelength then is the distance between the waves. Okay, we're going to learn about amplitude and frequency a little later, but for now, it's the distance between the waves. So the distance between the peaks or the distance between the troughs, which are the bottom parts of the wave. Wavelength is the distance of a wave, the length of a wave. What it is, length, wavelength of a wave. Distance from peak to peak, so peak to peak, or the distance from trough to trough. Water trough, or food trough, for animals to eat and drink out of. Trough, pronounce it trough. That's the bottom, and these are the peaks. Electromagnetic spectrum shows light waves, and the light waves differ based on their wavelengths. So some are more powerful than others because of their wavelengths. So let's look at the electromagnetic spectrum. Waves are really oscillations. So it means it goes up and down, up and down. Think of a slinky. So you hold both ends of the slinky and with one end up and down, you see a wave pattern going throughout the slinky. Waves are oscillations, so it's moving up and down. They carry energy. So energy travels through these waves. Two main types of waves. Mechanical waves actually travel through matter. So there have to be something it travels through. Electromagnetic waves can travel through a vacuum. So this is why sound is actually a mechanical wave. It needs to have something to travel through. So in space, when there's no matter, like in a vacuum, you wouldn't hear any sound. So it's silent in space. There's no sound. You could be screaming, "Ah!" Nobody'd hear you. In space, you wouldn't be heard. Because the sound waves have to have a medium to travel through. They gotta have something to pass through. They need matter to pass through. Electromagnetic waves, however, or light waves, they can pass through space. They can pass through a vacuum. They're actually the only type of energy or waves that can pass through in a vacuum. They can pass through space. So if you think of a vacuum, like a vacuum cleaner, it sucks up all the matter. So a vacuum, there's no matter. It's just space. That's what we call space, because there's a lot of space. Electromagnetic waves can be represented using an electromagnetic spectrum. And electromagnetic waves are often called just light waves, even though not all the light is visible. It's like X-rays. There's a part of the electromagnetic spectrum that includes the visible light waves, and it's a real small part. And that's what we can see. So there's many light waves we can't see. Light waves travel in a 90-degree angle from the motion of the wave. So if you think of a slinky, I'm holding a slinky out, and I take one end and I move it up and down. I'm moving this way, right? But the wave is traveling through the slinky this direction. So that means the wave itself, going up and down, is perpendicular or at a 90-degree angle to the direction the wave's traveling. So the direction the wave's going this way, but I'm moving, the wave's going up and down this way. So the wave goes up and down like this, but it's traveling this direction. So it's perpendicular. Transverse waves. Electromagnetic waves are transverse waves. Electromagnetic spectrum shows the different forms of light we have, even though it's not all visible. So we can see here the picture of it. We have the wavelength. This is approximate. This is in meters. So again, remember, this is going to be the distance of the wave. This is a 10 to the 4th meter, all the way down to 10 to the negative 12th meter. So these over here, you can see, look at the waves. Longer wavelength gets shorter, 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 shorter. The longer wavelengths have lower energy. So the longer wavelengths, lower energy. Lower frequency, lower energy. The shorter wavelengths have much more energy. So they have higher frequency, higher energy, packed with energy. So some types of waves we see here, the longest wavelengths are the radio waves. And these can be thousands of meters long. The microwaves are next. Infrared waves. And visible waves. So you can see here, of all the light waves, of all the types of light waves, we only see a very, very small part of the entire electromagnetic spectrum. Just the visible part, just here. So this is the white light we see. And the white light then is actually made up of all the colors. But just this one part of the entire electromagnetic spectrum is actually visible to us. UV, ultraviolet, and it's been studied that birds can actually see UV light waves. So they can see visible and UV. X-rays are more powerful, and some X-rays can be just as strong as gamma rays. So sometimes this can extend, the X-rays can extend. And the most powerful are the X-rays and the gamma rays. So they're the shortest wavelengths, high frequency, lots of energy. So when we look at the visible part. This is the only part, just this part of the entire electromagnetic spectrum is what we can actually see. And this is the visible light. So when we look at something, the colors we see is actually due to the length of the waves. So in just this visible area, there are parts, some of those waves are a little longer than others. So if we zoomed in on this one section here, the longer wavelengths are going to be like the red. Shorter ones will be more the violet. So this is kinetic energy because it's moving. The energy is moving in the form of waves, through waves. The next type of kinetic energy, the second type, is thermal energy. And thermal energy is how much the atoms are vibrating. So we measure that when we take the temperature. The vibration of the atoms. So this is kinetic energy because the atoms are moving. So remember, kinetic energy is energy of motion. Remember the pool balls. Remember I showed you this was like the indication of a solid. If we were zooming in on a solid, on the individual atoms in a solid, the atoms are actually vibrating. So that vibration is thermal energy. This is a form of kinetic energy because they're moving. The higher the temperature, the more they're moving. So liquids have more thermal energy. Gases even more, right? Because there's more vibration of the atoms. So they're vibrating more. The third type of kinetic energy that really is most common, makes sense, is motion energy. Because really kinetic energy is energy of motion. So motion energy is a third type of kinetic energy. When we look at motion energy, going back to the roller coaster, because the roller coaster is a really awesome example of the law of conservation of energy. Because you're starting with, at the very top at the lift hill, the maximum height, maximum potential energy. However, that potential energy then is converted to kinetic energy when you go down the hill. Woo! You go down, get the kinetic energy of motion energy. So there's a formula we use to determine the kinetic energy of motion. All right, and that is kinetic energy is equal to 1/2 m, which is the mass, times v, which is the velocity. So remember, velocity is speed with direction. So the mass in kilograms, the velocity in meters per second. If we think about a roller coaster, at the very top, maximum potential energy. At the very bottom, maximum kinetic energy. So as you're going down the hill, you speed up, speed up, speed up, speed up. Maximum. Once you hit the bottom, it's like their maximum speed. So you can calculate kinetic energy, how much kinetic energy there is, if you know the mass. Let's say we know the mass of the roller coaster, and we know its velocity. We know the speed. In this case, when we're looking at using velocity, we would use the same formula as the speed formula, which is the same formula for speed and velocity. So distance divided by time. So if we know the velocity and we know the mass of the roller coaster, we can figure out what the kinetic energy is.